You've probably heard quite a lot about the idea of space-based power, where you put up a bunch of solar collecting arrays and then you beam the power down to space through microwaves. And it's going to be complicated and expensive to do that. And you're always sort of comparing that to just make more solar panels or build batteries or wires here on Earth. And it's going to be a while before it's really competitive with Earth-based solar power. But there's an interesting idea that I ran into to use reflectors in space that would reflect sunlight down onto Earth-based solar farms. And maybe you can extend their day length and provide more power. So my guest today is Dr. Onur Celik. He is a postdoctoral researcher at the University of Glasgow. He focuses on space technology, and he has done research into would reflectors work? And so imagine you've got this big space satellite, like a big solar sail in space, that is directing itself towards various solar farms and reflecting the sunlight directly at them, but then also sort of turning itself edgewise when it's not needed, so it's not causing sky glare. So some interesting possibilities, and not just for the Earth, but also from other places around the solar system. So enjoy this interview about space reflectors. So when we think about power coming from space, like the traditional idea is like some big satellite in space that is collecting power and then beaming it down to Earth with some kind of microwaves. But you're suggesting something a little different.
Yes. So what we suggest is essentially reflecting sunlight from space, because the sunlight is always available in space, but because the Earth rotates, essentially, solar power farms stay idle after in evening or early morning hours, where there's a lot of demand for electricity, but there's very little contribution from solar energy because we simply don't have enough of it. So the idea is to use these large reflectors, lightweight and thin sort of aluminum foil-like reflectors in orbit, and angle them in such a way that capture that sunlight in space and reflect it to the Earth. And in that sense, I think it's a different concept than what is proposed generally by satellites.
And you wrote an article about this in the conversation, and there was actually a test of this back in the 80s. I didn't know about that.
Yes, but the concept historically is very old, actually, and even before the modern space era. The first mention of the concept goes back to Hermann Oberth's, the pioneer rocket scientist Hermann Oberth's book, Ways to Spaceflight, which was translated by NASA sometime in, I believe, 60s or 70s. And there is a mention of large reflectors illuminating airports, ship routes, and things like that. And the concept actually got some interest by NASA in late 60s to early 80s, with the hope of space shuttle bringing the cost down to launching things into space. And I believe in the 70s, also the oil crisis somehow affected the sort of this interest towards renewables and perhaps space-based solutions. And it's also around the same time where the other concept, solar power satellites, are also being sort of proposed. And on and off, the concepts got some traction in 80s and early 90s. Russia studied this in the early 90s, and it was actually some kind of a solar sail test and also a solar power test as an application of these like large reflectors in space. And they are actually, they succeeded, essentially. They put a 20-meter reflector unfurled from Progress spacecraft, which is servicing spacecraft to Mir space station at the time. And it's been tested, and I think in the news, the New York Times published a news about it, and there were some concerning readers also writing back to the New York Times as well, concerned readers, and there were more proposals in the Russian space program. There was another reflector that is launched. I think just before the 2000, it was a 25-meter reflector, which unfortunately snagged in the deployment mechanism, and then the program stops, I believe, because of the Russian space program losing interest in this. But the ultimate proposal was to launch things in 60, 70 meters and even up to 200-meter large reflectors to use it for this purpose or as solar sailing as well. So this was a long explanation to your short
Right.
question, but
Yeah, no,
yes,
but it's I mean, the thing that's kind of interesting is that it's essentially the same technology, that it's a solar sail. And
yeah,
the thing that would be used for potentially propulsion
exactly,
could also be used for reflecting light to some destination to provide power. And
exactly, yeah,
yeah, and like I think about places like the moon,
yeah.
where we have the need, we have 2 weeks of darkness, and any rover spacecraft that's on the surface of the moon is now out of energy waiting for the sun to come back, and this is when they die. And if there's be a way to reflect power light at them to fill their solar panels, maybe we could prevent that.
I'm glad you brought up this because I was going to bring it up at some point. Yes, I mean I think where we need energies is another place where we need energies is the moon and Mars and anywhere really. Either humans or uncrewed systems are going. We will eventually needing. Energy. And when you think about lunar surface and lunar darkness, when you have a rover or maybe there's an astronaut moving around in a little rover as well, or you have a settlement where we will need power. So reflectors like this could provide that sunlight, and also it's a raw form of energy as well. So it could be heat when a rover is too cold to keep it warm, as well as illumination in the sense that astronauts could use it for for various operations on the surface. And again, other rovers could also use it in the lunar caves when they were looking for water or water ice, and I don't know, bottoms of craters where you might need illumination to guide your landers. So there are many, I think, applications if you have I don't know, constellation of reflectors around the moon, if you wish, in the future.
And so, I mean, so let's imagine that you put some of these reflectors into orbit around Earth, and their job is to reflect sunlight at the solar farms on Earth to give them more power. What kind of extension to a solar panel's light collecting time do you sort of anticipate?
Yeah, so it really depends on the altitude that you launch things. So in our studies, we've looked at relatively lower orbits around the Earth, and the reason for it is that we are only considering flat reflectors, and what that means is that once you capture the sunlight and reflect it onto the surface of the Earth, your solar power, your image of the solar disk will be much larger than the reflector itself, and the solar power density will be low. And if you go higher orbits, then solar power density goes lower. So the system somehow favors a lower altitude unless you make your reflector larger. And so for that reason, we've looked at something about 900, 1,000 kilometer altitude orbit, which is about twice the altitude of International Space Station, essentially. And in that case, we get about 20 minutes or so of an extension to the energy generation. This sounds a little bit short, and I'm aware of that, but a couple of reflectors just added in a constellation could essentially extend this all the way up a couple of hours, both before and after sunset or before and after sunrise. Such that we could extend this electricity generation times of where the electricity demand is higher and the prices are higher as well. So this is generally compensated by fossil fuels when renewables are not sufficient, like such as wind or the sun. So these reflectors could potentially provide some sunlight that turns into electricity.
And so would one reflector be, as it's orbiting at that 1,000 kilometer altitude, is it sort of hitting one solar farm and then it's hitting the next one and then it's hitting the next one? Is that sort of the approach?
Yes. So I believe one different thing from generally the traditional sort of solar power satellite is that reflectors are essentially decoupled or independent from terrestrial solar power infrastructure. So as the spacecraft orbits, the Earth rotates underneath. So that means the sort of ground trace of the orbit can, well, if there is a solar power farm or any sort of ground target that needs to turn sunlight into to energy, electricity, they can use this system essentially. So some of our studies, we've also considered some hypothetical solar PV farms around the Earth, and 20 and maybe more solar PV farms could be possible to service, such that they can both day and sort of early night hours continue to generate energy.
And how big is this sail, this reflective sail, going to be to sort of nicely match the size of a solar farm?
So essentially, the reflectors that we are considering will really, because of the solar image or the projected sort of illuminated area on ground, they operate best with the ultra large solar power farms. So sort of individual rooftop solar panels won't be the target for these systems, but really ultra large systems, kilometers and kilometers wide, perhaps. So and to generate meaningful electricity, we kind of consider in our study about 250-meter sort of side lengths, hexagonal reflectors. Hexagonal, that choice is more structural and design choice, but it could be a circular shape as well in that case, or a square for that matter. And in our study, we've looked at 5 of those. That gives approximately an area of 1 kilometer diameter circle. And that generates about 35 megawatt hours per pass. And that's something about, I think in UK, I'll give an example from UK, and I don't know how it works in other places, but it's about the average sort of electricity use per year for a home. So it can actually power up some hundreds and maybe thousands of homes with a couple of extra reflectors. So the numbers obviously varies based on electricity use by homes, but yeah, this is.
So I'm kind of imagining. So these would be like attached hexagonal. I'm sort of imagining something like the James Webb Space Telescope's main mirror, but as a giant solar sail floating in space, reflecting sunlight down to Earth. But I guess that's seven hexagons as opposed to 5.
Yeah, I mean, approximately. I think our design looks quite similar to what that main mirror of James Webb Space Telescope, except that it's much larger. Yes, and the choice of that was motivated mostly because it's easier to bring multiple triangles, same units of triangles together, if you are to use in space assembly or manufacturing. That kind of it's a more sort of a future outlook for the concept.
But like, would this fit within, say, one launch fairing of a rocket?
Yes, for in our designs, we've I think everyone is looking at Starship at the moment, and in our design we kind of limited our maximum size based on Starship fairing. So we imagine in a sort of a folded configuration, this will fit in Starship, but I think it really depends on if Starship is going to fly or not eventually.
Sure. Yeah, right. But the point is that you would build a like each one of these reflectors would fit up inside a starship, or maybe the smaller version would fit inside a traditional 5-meter fairing, and then it would be launched to that orbit, and then it would deploy, and now you would be getting the reflective power of this. So from just like a doing the math perspective, right? The traditional idea is we build a solar panel array in space. It's collecting power, it's storing it locally, it's then beaming it down to Earth somehow with a microwave at some receiving station, sort of a different machine in terms of like being able to generate power. So did you like just compare the price per watt, I don't know, from your strategy versus kind of like these traditional ideas of power generation?
I don't know if there's it could be directly comparable, because I think the sort of building of solar power satellite goes hand in hand with the ground system as well. In our case, it's a little bit different and potentially cheaper. I'm saying this cautiously because obviously in space development, we don't never really know how expensive things can be all of a sudden. Cautiously, I'm saying that it could potentially be cheaper. It's a relatively simpler approach and relatively simpler system. And technically speaking, solar sails have been launched in space as well. But there are many challenges because it's a massive system that hasn't. It's larger than International Space Station if you think about it, and there are control challenges that technologies that need to be developed. There are other issues in terms of potentially regulatory issues related to launching something large into space in this way. So I think this all brings levels of cost that we cannot really predict at the moment. But I think it could potentially offer a cheaper alternative. But I'm saying this cautiously, so I don't want to.
Right. Well, I think it's safe to say, because like the estimations for power generation from space are just like still sort of ludicrous.
Yeah.
And there's like no model where it makes more sense to try and generate your power from space than to add another solar panel. And I guess that's what you're really competing with is, does it make more sense to try to reflect the light, or does it make more sense just to add more solar panels, or maybe build wires from places that are still in sunlight to the places that are in darkness?
I mean, ultimately, the sun is really the closest thing we have to infinite energy. It's because it's going to be there for another couple of billions of years. But Earth is rotating. Eventually, solar power farms will not generate electricity when there's no sunlight. I haven't run it personally, but in our research group, we've run a study on comparison between energy storage and orbiting solar reflectors. And in some cases, actually, solar reflectors could turn out to be more profitable than energy storage. And in those cases, I guess you save some space with energy storage and also potentially money. And there's some, sort of carbon cost of that as well. Something I refer to NASA study in that case as well. But ultimately, there are cases where solar reflectors could prove more profitable than putting more solar power farms. But I think ultimately we should put more solar power farms. We could still put reflectors in space and illuminate them and continue generating even more renewable energy while reducing our fossil fuel reliance, I think. So
yeah, I guess like in the future, like right now, obviously, when the sun goes down, then your solar panels don't work. But if you've got a really nice network between solar panels around the Earth, then as some are in shadow, others are in light, and you're connecting them up. And so maybe, I know it's kind of hard to get power conduits across the Pacific Ocean to supply Europe.
I think there's that issue as well. If you are sort of transmitting power with cables for longer distances, you are also losing along the way. And also that is expensive too. I think there's a number of projects around the world, kind of connecting underwater, like electricity through underwater. There's one between UK and Morocco. There's another one between Australia and Singapore. So there's a number of projects, but they're also quite costly if you think about it. And there's also a lot of loss in transmitting as well. So maybe the energy people won't like what I'm saying, so I don't want to go too much. But yeah, I think there's a benefit in employing potentially space-based systems as well.
And so let's talk about sort of like how it's going to be perceived from the surface of the planet.
Mm-hmm.
Now, your proposal is that you're only adding really just a few minutes to each solar panel, because that's just how long you're in sunlight for before the solar panels are in, or before the reflector is in shadow too. So, if you're standing on the ground and the sun goes down and now you're not getting energy under your solar panels, but now you're seeing the reflector, how long will you see it before it also is no longer visible?
So the total pass duration in lower Earth orbits is about 15, 20 minutes. So this is the time that reflectors could potentially be visible. But the brightest part of the illumination will be when it is close to the sort of overhead or like zenith point, which is about, in those altitudes, about 3 or 4 minutes in total. Yeah.
But it'll be still twilight. Like, it won't be dark. It'll be the sun has just gone down, and for 20 minutes, half an hour after the sun has gone down, you're still seeing this thing going across the sky.
Yeah, I think my imagination from the results I get is that unless you're very close to it, I don't think it will be actually visible. There might be a little. It might look like a little bit of a star, and that geometric sort of calculation that either doesn't also tell us that it will be too bright and too big. And I think obviously in the videos in the conversation article, there's like a nice sort of night view which looks quite illuminated. But I think in sunrise, like just before sunrise and just after sunset, there's still a lot of illumination. The sky is still quite bright. And maximum we estimate illumination or brightness would be is about overcast day. So maybe a little bit darker than how my background is right now.
Right.
If you could see it, yeah.
But you're expecting that it would be more targeted. So
yes,
wherever it's going to be targeted to where the solar farm is.
Absolutely,
they're going to be the people experiencing the brighter light, but not necessarily people outside of that.
Yeah, so I mean, because of the geometry, there will be parts where the illumination will be outside of solar power farm as well. But ultimately, as the reflector goes overhead, that gets really small, and depending on the size of the solar power farm, obviously. But if it's large enough, it's completely contained within the solar PV farm. So ultimately, no one around it could really experience that additional light either. Maybe just the solar panels. At least that's
right. But it's not hovering in space. It is orbiting at that 1,000 kilometer, unless it's within geosynchronous orbit.
Yeah.
It's going to be moving.
Yeah.
And so for some number of minutes, it's going to be over top of the solar farm, but then it's going to be to the north of the solar farm or to the south of the solar farm. And so if you're in that, like, is there going to be, like, for people on the ground experiencing this, if you're on the track, I sort of think about it like if you're going to try and watch a solar eclipse, and if you're on the track of the solar eclipse, then you can see the solar eclipse, the entire track through. Yeah. Is it like that if you're on that track, you're going to see the brighter surroundings?
Yeah. So again, in much lower altitudes, I explained the situation when we are overhead, but in much lower sort of elevations, sorry, in much lower elevations, the solar image or the illuminated area will be extremely stretched. So it will be much larger at times than a solar power farm. But I think we need to also consider the fact that we always capture the same amount of energy in space. And when you sort of distribute it in a much larger area, the brightness becomes even less. So in the much lower elevations, actually the brightness decreases in levels that might not be even recognized or realized, realized by anyone, even around the solar power farm. I think
So
there's that too.
right. So sorry, just trying to understand. So
Yeah.
so it is orienting itself
Hmm.
during its orbit to remain focused on the solar farm as it makes its pass in the area.
Yes.
Is that it? Like it is actually, it does have control. So it is attempting to point its reflection at the solar farm for as long as it can, and then in theory it'll have a different target and then reorient itself into a different direction. Is that so? It's not just a static fixed reflector in space that's just casting a beam. It is actually trying to target itself to wherever the power is needed.
Yeah, so
Yeah. Okay.
it essentially sort of moves around the solar PV farm. It captures the sunlight and reflects it. Well, in our modeling, it's the center of solar PV farm, but it's the solar PV farm that we are targeting, and the orientation is just following
Right.
that. Uh, yeah, so there's
I mean, because
no
I think about
just yeah.
like when the International Space Station flies overhead, and then you see it pop up in the in the west, and it flies overhead, and it's this bright star that goes across the sky, and then it fades. But if it, I guess, if the International Space Station was completely dark, but it had one reflector that it was aiming at me,
Mhm.
right, the entire time, then I would see it. But maybe a friend who's just a few kilometers away from me wouldn't see it
Yeah,
because
so I'll go back to that Russian experiment. So there are the reports. So obviously, I was very small, so I don't remember any of it. But there are reports that because that experiment was just it wasn't pointing anywhere. It was just capturing sunlight, and it was in the overhead position, like International Space Station at all times. So it was a circular illuminated area, just traveled across the face of the Earth in that case. What we are trying to do is different than that. So we completely orient the reflector to a service or illuminate the solar power farm for a given duration. And then we sort of angle away and sort of actually go edge on to the sun. So actually nothing is reflected in principle. So that's the idea of the reflectors that we are proposing.
right, and that's that is the concern from the astronomical community with the
Hmm.
rise of these satellite mega constellations, is that these things are more like that International Space Station example. They're flying overhead. They're not, they're leaking light in all directions, and they just are casting these illuminations. But so in your from your perspective, you're going to say, okay, no, we're going to respect where the observatories are, make sure that we aren't directing our light anywhere near them. Like it's going to be hopefully in collaboration with the astronomical
Yeah.
community.
Yeah, so I think the difference with, for example, Starlink constellation, it is, it was reflective on the solar panels, and there's no way that they can angle away to not be visible, I think. So we took these regulatory and environmental issues in the best way that we can approach with the skill set we have from the very beginning. So the control strategy that we developed and shared it in that technical paper actually included sort of as soon as the operation is finished, we go edge on, such that in principle no light is reflected to the ground. So this is something that we consider when we are doing our studies, and we accept that these are legitimate concerns, and we try to bring up numbers, do our modeling, and try to answer as much of those questions as possible. And I think when it comes to solar power farms and astronomical observatories, that too, so to my understanding, there's usually not a lot of overlap between those two places, because solar power farms need to be relatively accessible, whereas astronomical sort of observatories are very high up and actually, dark and remote places. And I think there's a I mean, there could be one solar power farm very close to that observatory that I don't know, but I think, to my understanding, there's generally not a lot of overlap between those two. And with the sort of operational approach that we try to bring, hopefully these concerns will be answered as well.
Right. So we talked briefly about this idea of like supplying power to the moon. You sort of listed off a bunch of ideas as well about illuminating, caves on Mars and things like that. So where do you sort of see some of the other applications for this kind of reflective power supply?
I think, Mars could be possible, a possible application. I think there's because the Martian atmosphere is thinner than the Earth atmosphere, and because it's kind of like a smaller object, you have a longer time to deliver energy and less of the energy that is lost in the atmosphere. So there could be some interesting applications by illuminating sort of Martian bases, or illuminating landing spots, possibly of these rovers and so on. And other than that, there are these reflectors go into. If you just reflect the light away, you could use it for climate engineering type of solar geoengineering type of more sort of far term applications as well. These are some of the other things, obviously, other than solar sailing, which you could use and power your spacecraft.
One of the big problems in the outer solar system is that you're getting a lot less energy from the sun. Like when you're at Mars, I think it's like 1/4 the solar energy, maybe to half. When you're at Jupiter, it's like 1/25, and it gets even worse out at Saturn. So is there a like say you had a rover on the surface of Europa, either it's powered by a nuclear battery, or it's got just an enormous amount of solar panels that are dwarfing the thing, or maybe you put something in orbit that is reflecting sunlight down at it. And you're talking about what seems like more of like a flat reflection. Can you focus it? Could you say, so you did have that James Webb, those panels, right? Could you be beaming 7 panels worth of energy down to 1 panel's worth of receiving area?
Actually, I've done a mathematical modeling on this, and I actually looked at different planets. And it's going to be a little bit technical, and hopefully I'll try to explain it in as accessible as possible. So as you go away from the sun, obviously the sun's intensity is decreasing with roughly about the square of the distance that you're away from the sun. But at the same time, so the operation principle of reflectors, you don't assume the sunlight being completely parallel to the reflector, but there's because there's like a circular shape of the sun, you have this angular diameter, and that's why you get a larger image on the ground as well. So when you move away from the Earth, the angle sort of that's subtended by the sun on the reflector gets much smaller, and even though you sort of capture less energy, sometimes in some cases the illuminated area on ground is small enough that your solar power density is actually higher than closer places to the sun. So I'll give you an example. Obviously, for the moon and Earth, doesn't matter much because they are almost the same distance to the sun. But if you think about Mars, actually the solar power density gets a little bit higher, or the energy delivered to the surface, the quantity of energy delivered to the surface for the sort of same amount, same altitude, gets a little bit higher than the Earth because the atmosphere is thinner. Your angle, sort of that subtended by the sun, is smaller, so that your solar power density gets a little bit higher. It's kind of counterintuitive, but in some cases, in some planetary bodies, you can get a little bit higher energy than others that are closer to the sun. So it's not impossible to generate solar energy on Europa, which could be higher than, I don't know, some other body that's closer to the sun.
I think about in the Expanse TV show.
Yes,
they had at
right?
Ganymede, right? They had Ganymede. They had these reflecting light sort of in space that were reflecting sunlight down to the greenhouses on Ganymede, which was supplying the vegetables to the outer solar system, which I thought was really cool. And so I wonder, like, is there this, like, I wonder is, you know, there's this cost trade-off. And I know these studies have been done where it's like the farther you get from the sun, the more it starts to make sense to have a lens that is reflecting the sunlight and then concentrating it on your solar panels versus just having bigger and bigger and bigger solar panels. Like there's this cost benefit that switches over at a certain point in the solar system.
I haven't actually studied the concentration.
There's a bunch of papers. I've seen them in the past. So
I'm not going to. I'm not going to. So I cannot really give a definitive answer on this, but I don't know. I think so. I guess the sort of the area that you eliminate will be smaller as you go further in the solar system, and that means even if you make the solar panels or the area of solar farms bigger, I think there will be a point that parts of those solar panels won't be eliminated anyway. I think maybe there's a limit that focusing becomes better than just making bigger sort of solar power farms in outer solar system.
Yeah, and I know there's been some studies on this, and I forget the numbers exactly, but that at a certain point, I feel like beyond Saturn or something like that, that actually you make small solar panels and large reflectors that are concentrating the sunlight onto your small solar panels, because giant solar sails are less expensive than giant solar panels, and so there's this trade-off at a certain point for the complexity and all that. So
it's interesting. I didn't know. Sorry.
Future study. I'll see if I can dig up the papers and send them your way.
Sure.
So, Onur, what are you obsessed with right now?
I am obsessed with, I think, various solutions that we can come up with these reflectors. I can see a lot of possibilities in terms of space exploration where we can use these reflectors to power our satellites and illuminate solar power farms in Mars or the moon. And generally solve some of the, not solve, but at least address some of the energy problems that we have both on Earth or elsewhere with some space-based solutions. This space has been my passion since early years of my education. So it's, and I'm passionate about doing these.
Well, thank you so much for taking the time to chat with me today, and good luck with your research.
Thank you.
I hope you enjoyed this interview with Dr. Onur Celik. I'm going to give you a lot more thoughts about this, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Hey Twyla, Dougie Stewart, Stephen Krasaki, David Richards, Mark Anstis, Joel Yancey, Antonio Lofilara, Dustin Cable, Vlad Chiplin, Modso, George, David Gilton, Andrew M. Gross, Jeremy Mattern, Josh Schultz, and Jordan Young, who support us at the Master of the Universe level, and all of our other supporters on Patreon. Now, the focus of this interview is really about whether or not you can use these solar panels here on Earth to get more sunlight, the reflectors. That all sounds great. But I'm more interested in those fundamental technologies, like building giant solar sails, putting them in space, and then using that to reflect sunlight. It's the places away from the Earth where we don't have that infrastructure where this technology will could probably see its greatest benefit. Imagine being able to reflect sunlight down onto rovers on Mars so they don't have to have giant solar panels or nuclear batteries. You can just deliver them power on a regular basis. Or on the moon, where you're giving rovers power during the 2-week-long night on the surface of the moon. Farther out into the solar system, where maybe we're going to run out of these nuclear RTGs, the kinds of things that are powering up Curiosity and Perseverance. But instead, you can use reflectors onto solar panels. Missions to Europa, missions to Saturn, missions to Uranus, Neptune, maybe all the way out to Pluto. I mean, it's just a matter of like a larger solar sail. And yet that development of larger solar sail technology will have value for all kinds of things about us being able to eventually travel interstellar distances. So it sort of meets all kinds of things that I'm really interested in. So I hope you enjoyed it too. Now, I've done another interview just about solar power generation and beaming, but not down to Earth, but to other locations in space. And so if you're interested in sort of learning more about that, here's another interview for you. All right, we'll see you next time.